I have his biography, pages long. I just tried to shorten it a little bit. He is a fellow of IEEE, IFAC, AAAS, Institute Measurement Control, so on and so forth. And he is a UTA Distinguished Scholar Professor, UTA Distinguished Teaching Professor, Monchief O'Donnell Chair at the University of Texas Arlington Research Institute. He ranked H-index at position 84 worldwide as of last week, and 69 in the USA. Still, this was an old number, but something like that in the USF. This was one of the 100 researchers. And he obtained his Bachelor of Science degree in Physics EE and MS-ED from the Rice University, MS in Aerospace Engineering from the University of West Florida, and PhD from Georgia Tech. He has a lot of awards, almost every award one person can get, and including NSF Research Initiation Grant, ASEE Techman Award. Frank, I'm not going to go through all of this. You've got all the awards, I can say shortly. And he's an author of, he was listed by the Fort Worth Business Press, top 200 leaders in manufacturing. And he has 7 US patents, numerous journal special issues, 380 journal papers, 20 books. And Frank, we are ready. Again, thank you so much for your time coming here. It was our pleasure to have you here, and whenever you are ready, we are ready.
Tansel, teşekkür ederim. İyi günler, nasılsınız? It's really great to see Tansel and the Turkish students here. I've got a really close connection with Turkey. It's too bad you can't see this picture here on my screen. But I met her in the Bebek Hotel restaurant on New Year's Eve in Istanbul, Turkey, about 15 years ago. So it's really great to be here for bringing back memories. I spend a lot of time in China. The best way to get some research done is to disappear where nobody can find you. So I spend a lot of time in Hong Kong, and this presentation was actually written here. Okay, so this is cooperative control, optimality and gains on communication graphs. And the point of this is that most consensus and who's working on multi-agent control in here? Synchronization, consensus. Most of those algorithms are protocols that depend on the neighbor's states, but they're not optimal. They're not optimal design. So I'm going to show you that if you do optimal design of consensus protocols, you get a lot better results. So we're interested in the synchronized motion of groups of agents, and here biological agents synchronize, so fish school, birds flock, and the point is that the motion is different depending on the way you communicate. The quick darting motions of the fish, they ain't like the slow wheeling motions of the birds, so why not? It's because of the way they communicate. The birds can only see 1 or 2 people right in front of them, and the fish can sense 20 or so neighbors because of pressure waves. So as soon as one of those guys moves, they all go together. So the way you communicate influences the way your control system works. So you have to design your control system to take into account the communications protocols. Applications, traffic management, aircraft formation, platooning. So we wrote this book about cooperative control systems. And then we're going to talk about cooperative control, locally optimal design, globally optimal design. They're not the same. And then a thing we invented called graphical games, which is a multiplayer game that takes into account the communications network topology. Standard multiplayer games don't have a network topology. Oh, I can't show you this cool movie, it's not my computer. Okay, so a lot of you know about this. You have a communication graph. Every node can only communicate with a few of its neighbors. So these arrows should actually be directed arrows, but it was too much trouble to put them in PowerPoint. So you can imagine some of the arrows go one way, some go the other way. So this little guy right here can only get information from 1, 2, 3, 4 neighbors. This guy gets 3 neighbors, and yet there can be 1,000 nodes. So you have a controlled protocol that only depends on what you can see locally, and yet it's going to guarantee global synchronization of the whole group if you design it properly. So that means you can add nodes by connecting to a few other guys. It's scalable. You don't have to worry about how many nodes are in the network. All you got to do is worry about how many little guys you can see. It's called the n degree. So a special graph, a graph is strongly connected if you can get from any node to any other node by following the arrows. That's a very important property. There's a thing called a tree, which is the leader. He doesn't listen to anybody. The boss never listens to anybody. It's kind of like we're being recorded. I better not say it. That was going to make a joke. But the military likes that because it's very efficient. And there's a thing called a spanning tree, which means if there's one node that everybody else can see, he's the root of a spanning tree. And that's another important property. So given those two things, we want to, it's hard to analyze that picture. Nobody can analyze a picture. But you can analyze a matrix. So the first thing we do is make a matrix to represent that picture. So that means the same as that. An arrow from 1 to 2 means column 1, row 2's got an entry. 2 to 4, column 2, row 4's got an entry. They don't have to be ones. They can be anything, but generally positive. So that thing there captures the topology of the graph, and everybody and their grandmother knows how to find eigenvalues. So the eigenvalues of A are very important. So there's this thing called the row sum, which is how many arrows. Row 3 has got 2 arrows coming in. It's got 3 neighbors that it can see. So you can see the people at the other end of the arrows coming into you. That's the only information you're allowed to use to design a state feedback controller. So the row sum is the in degree. We do that. It's the control thing. The column sum is the out degree. It's how many people you influence. So this is having to do with social networks. People in control theory have not yet used the out degree to advantage. And I think it has important information that we need to look at. Okay, so we have a local voting protocol which says if you look at your neighbor's state, if you can see him, if he's a neighbor of yours, Aij is non-zero, so there's an arrow coming in. And if you can see that guy, xj, you measure his state. Xj minus xi is how different you are from that guy. And you try to make yourself the same as all your neighbors. So you're in a formation. I can see that guy, I can see her. We're driving our cars. I'm trying to match my headings to their headings. So I'm trying to average out the difference between him and her and match it up. And they're doing weird stuff. It's like he's all over the map. She's all over the map. Why? Because they got neighbors. And I can't see the neighbors' neighbors. So I can only see the people right next to me, and I can only use their states and try to match my state to their state if they're my neighbors. But they're doing the same to their neighbors, and if the graph is strongly connected, everybody can see everybody. Eventually everyone comes to the same heading and speed. So this is called the local voting protocol, and xi dot is equal to that. So if you're the same as your neighbor, you don't have to adjust. But if you're not, you try to adjust. There's a minus, it's negative feedback, it's stable. Xi dot is minus xi. So if you do a global thing there, so control 1, control 2, agent 3, agent capital N, could be 100 of them. That is one line in a matrix. And if you take the xi out, you get the in degree, which I just mentioned, it's the row sum. And you get the A matrix here, and the nutshell is that if everyone does that, the formations dynamics look like this. So I can analyze the formations dynamics in terms of this matrix D, which comes from the second term, and A, which comes from the first. D minus A is called the Laplacian. So the Laplacian is a very important matrix having to do with that graph. And it captures the graph structure if everybody uses that protocol. So 98% of the papers in consensus and distributed control use that protocol. But it ain't optimal, and it can get you in trouble. So the graph Laplacian is D minus A. Next idea is you can have a leader. So there's a neighborhood, everyone's trying to average their opinions to their neighbors, maybe a small town. And some politician comes to town, and he wants to influence the local behavior. So who does he tie into? If he can tie into a few influential nodes, and then everyone can listen to those guys, he can hijack the opinions of the entire group. So this is a big deal in social networks. And the question is, who do you tie into to have the maximal impact? But the way we use it is that X0 is, for example, a formation leader. And if he ties into a root node, somebody that everybody can see, at least one root node, he doesn't have to tie into too many people. You can have a network of 1, 2, 3, 4, 45, 50 people. All I got to do is talk to her if I know that she can eventually influence everybody in the room. So not many people have to directly see the leader. So that adds a term to the previous protocol. If you can see the leader, Gi non-zero, you try to match him as well, and that gives you the matrix L plus G, Laplacian plus the leader's pinning control. So that guy's important, and everybody and their grandmother in a distributed control knows how to do stuff based on those ideas. So let's talk about stable design versus optimal design. Take a break, cool picture. The graph eigenvalues are different for different structures. The tree has a very good structure. All the eigenvalues are at 1, which means minus L has them all at -1, and e to the minus t is an exponential term that makes you go to the leader very quickly. If you have these gossip rings, military uses that. We use this in our daily lives. If you use that, I talk to her, she talks to him, you don't go to dinner with everybody at the same time. You go to dinner with one person. And I tell him, he tells him, around and around and around, and it comes back to me. It's like, that's not what I said. Somebody's lying, who are you telling me? And we go around about 10 times, and you oscillate until you finally get to consensus. Because the eigenvalues of the gossip ring and the plane, complex plane, are uniformly spaced around a circle. So they're imaginary, so they oscillate. You've got to be careful how you pick your communication network. Take a break, cool picture. Now, here's a graph. Looks innocuous. 6 little guys with 1 leader. Information flows, so if you, number 2, can do that protocol I showed you using x1 minus x2 and x6 minus x2. And so if it does the naive thing, which is it's a vehicle, it picks a feedback gain to make its own heading stable. So its dynamics are AX plus BU. Everyone's got the same dynamics. And you design a local feedback controller to make A minus BK stable using, for example, LQR design or Riccati design, whatever you want to use. You can make A minus BK stable, but if you pick the wrong kind of stability, you're screwed. Here's what happens here. In that graph, everybody uses this protocol, which I told you about already, tries to match your neighbor's heading. And so this is the XY plane. So that dynamics is a vehicle. So everyone starts at a different heading, but eventually they all synchronize because that graph is strongly connected. So you all come to the same state. They all come to the same heading, and they all go off into the sunset in a formation together. So there's a graph, there's 6 of us, that structure works. Now suppose I suddenly start talking to that guy back there who I wasn't talking to before. So I add another link. Should be better, right? You add another link, more communication in the graph. What happens? You totally destroy the synchronization. Nobody synchronizes. Another link screws you up. You don't synchronize to the headings, and you don't make a formation. So what's the deal about that? So even though you pick the feedback to make A minus BK stable, to make a feedback like an autopilot for your car, heading control, if it makes your car work, and if you start talking in a certain graph, it means everyone reaches the same formation, heading, and speed. But if you start talking about the wrong kind of graph, too much information, your stable controller goes haywire when you start connecting to other people. So that's not cool. So how do we fix it? We want to pick K in such a manner that you get formation stability on any graph, it doesn't matter the topology. We need to design A minus BK in a certain way. You can't just pick A minus BK stable, as this counterexample shows. So how do we pick K, the local gain, to make it work on any graph, regardless of how I communicate with the other people? Okay, here we have a leader. We have our dynamics, xi dot is axi plus bui. Everybody's the same, it's called homogeneous. There's a really interesting problem called heterogeneous, which is where different kinds of vehicles try to synchronize. And that's really cool, it's called the output regulation problem. Really interesting results on that. Current topic of research. You've got a leader, x0 dot is ax0, who's moving. And you want the formation to follow the leader, and you use that same little law that I showed you before. Everyone tries to synchronize to their neighbors if they can see them. In the graph, you see a few neighbors. If you can see the leader, you synchronize to that guy. If not, you just worry about your neighbors. But the graph is strongly connected, so eventually the leader's information can percolate through the graph at some point. And what you do is you make the global thing the way I showed you in terms of the Laplacian, d minus a, and you get the global error dynamics. I met this guy at the NSF, Paul Ribos. He gave us some funding. He was a computer science guy. He said, Frank, you know, controls guys are the most boring people in the world. All you do is you find the aerodynamics and make it stable. Probably it's true. If you can find the right aerodynamics and stabilize them in the correct way, you can pretty much rule the world as a control theorist. You can design, well, who invented the steam engine? Don't say James Watt. It's not James Watt. Thomas Newcomen did. You ever heard that name? Nobody's ever heard that name. He invented it in 1712. James Watt invented the controller that made the steam engine useful 50 years later. So control is a big deal. So what you can do, you can show that if you have a graph, and everyone uses that local protocol, that A minus BK being stable is not good enough. You can't just pick A minus BK stable, that don't work. You have to pick can you see that? A minus lambda BK has to be stable for every lambda, which is an eigenvalue of the graph communication matrix. So you pick the graph Laplacian, that depends on the topology and who can see the leader. And you look for the eigenvalues of the graph topology, the eigenvalues of L plus G. And I showed you for the gossip ring, they're complex. So you get all this oscillation. Whereas for the tree, they're really good, e to the minus t. So you can't just stabilize A minus BK, you've got to stabilize A minus lambda I BK for every lambda that depends, that's a graph eigenvalue. So the control A minus BK design depends on the graph topology through the lambdas, which are the eigenvalues of the Laplacian, assuming everybody uses that law. So this is a big problem, because to pick your K matrix, you've got to know the graph topology. You've got to know how you're going to be talking to people before you can design your autopilot for the car. Well, that's not cool, because you don't know who you're going to be talking to the next day. So I'm going to figure a way to pick that K so that that condition holds no matter which graph I'm talking on. And I showed you before the lambdas of that first graph were good, and this condition was satisfied by chance for the K I happened to pick. But if I put the other graph, the link, it changes the lambdas. And so now that condition is not holding for the new graph. So how do I design K to make this hold regardless of lambda, the graph topology? I love optimal control. If everybody does locally optimal design, everyone solves a linear quadratic regulator locally based on a performance index, minimum energy, by solving a Riccati equation, which MATLAB's routine LQR does that. If everyone does locally optimal design, then that condition holds for every graph, doesn't matter how you talk, as long as you pick that C big enough, which is the coupling gain. You've got to be listening to your neighbors with at least a minimum amount of attention. And that C depends on the maximum real part of the minimum real part of the eigenvalues of L plus G. So you only have to know general information about the graph, not the detailed eigenvalues of that matrix. So the key to being stable on every graph is to do optimal design for every agent. And you can all have different objectives, pick different Q's and R's, and do different, like I'm worried about my gasoline, she's worried about not being too jerky on the steering wheel, different objectives. As long as you do optimal design, it works. Doesn't matter how you talk to people. Proof is cool. It's based on some Lyapunov theory. What happened in 1957? Sputnik. Who set up Sputnik? The Russians, not the Western world. Why? Because we were screwing around in the US with linear design because of frequency domain techniques that were invented at Bell Labs 30 years earlier. And they worked fine through World War II, but spacecraft ain't linear. The Russians could at that time do nonlinear design because of this guy, Alexander Lyapunov, who lived in 1892. So Lyapunov theory is a controlled design method for nonlinear systems that works for spacecraft. So they put up the first spacecraft. 3 years later, Rudolf Kalman wrote 3 papers. One of them said, we need to look at optimal control, optimal performance design. 2, we need to go look at Lyapunov's theory. I won't tell you what the 3rd paper was. Keep you guessing. So as long as you do locally optimal design using MATLAB routine LQR, for example, and worry about your optimal performance, then no matter how you communicate, you're going to get a good performance. As long as you pick that C bigger than 1 over lambda min of the graph topology L plus G. Why? There's a thing called region of synchronization. And if I pick that K that I showed you, A minus BK, it turns out that that condition, A minus C lambda I BK, it holds if the graph eigenvalues are in a certain region for that bad K. So the lambdas are restricted. That bad K I picked where I showed you that it goes to pot if you put that extra link, the graph eigenvalues have to be inside that region. Evidently the first graph had them. But I put that extra link, suddenly they popped out of that region and don't work. So the optimal design I showed you, the synchronization region is an infinite right half plane. So as long as the graphs have eigenvalues anywhere in there, it's going to work. So every graph has eigenvalues in there. If you crank the gain up to make this thing go further to the left, if you do optimal design. Okay. Cool. Take a break. Discrete time case. Let's look at the discrete time case. And you remember the thing I just showed you, you decouple the local controls design from the graph topology by doing optimal design and picking that coupling gain. So I got to listen to her enough. I got to regard him enough. I can't just think, oh, I kind of want to do. You got to be at least tightly coupled enough to your neighbors to make this work. Plus, you got to do locally optimal minimum energy, minimum fuel, some kind of optimal design. So let's look at the discrete case. xk plus 1 is axk, buk. Everyone's got the same ABC, homogeneous. Everyone uses the same little, can you guys see this in the back? I hope so. Local voting protocol, try to match your neighbor's state. If you can see him, EIJ is non-zero. I only had to talk to a few people. It doesn't matter how many people are in the room as long as the graph is strongly connected. And if I see the leader, I take him into account. And I use a special protocol called normalized for discrete time. And then I do the closed loop stuff, and I get this global graph matrix L plus G, which describes the whole formation behavior if everybody does that law. And I can do the same thing I did before, and what happens is, you get the same condition, A minus C lambda I BK has to be stable for every lambda in the graph topology L plus G. But what does stable mean for discrete time? It means inside the unit circle. The unit circle ain't very big. In the continuous time case, it means anywhere in the right and left half plane, which is a lot easier to deal with. So what you end up with is you have to do a locally optimal discrete time design, pick the gain according to the discrete time LQR, and you have to define this R, which is based on dynamics AB, and your performance QR, which is in your performance index. That R is your local design parameter, and it defines a radius of a circle. And all of the graph eigenvalues have to be inside of a circle, which can be projected inside that circle. So this circle has to do with your locally optimal design. This has to do with the graph topology. We're trying to keep them apart. I don't want to have to know the graph topology to design my controller. So if I design the controller optimally, and I design this parameter, and draw a circle, that depends on the way I design my controller. And the graph has its eigenvalues in here, real part, imaginary part, the Laplacian, that's the topology. You've got to be able to project the graph covering circle inside that. So if I know the graph topology, I can pick R big enough, but I don't know that, right? So this is a little bit of a more complicated thing in the discrete case because you're trying to get all the stuff inside the unit circle. So what does it mean? In the single input case with real graph eigenvalues, you can define, it means this. There's a thing called a Mahler measure. You guys know what the Mahler measure is? You look at all the unstable eigenvalues of your dynamics, and you take the product of the real parts of all the unstable poles. That's called the Mahler measure. And that depends on my dynamics. Lambda max plus lambda min over lambda max minus lambda min, the right side depends on the graph. And those lambdas are the eigenvalues of L plus G, the graph topology. And if the topology changes, that thing changes. So this captures how the local design has to keep up with the way we communicate. The way we control depends on the way we communicate. What does it mean? The Mahler measure is the product of the unstable eigenvalues. You take the log of that, you get something called topological entropy. And that depends how badly my stability properties are. If I'm stable, that's not a problem. But if I've got instability in my dynamics, this topological entropy has got a problem. And over the right-hand side, I can define something which I haven't seen designed before, called the graph condition number, lambda max over lambda min of the topology. If the topology is good, like a tree, that guy is, what happened? It came out of the presentation. There's always a button where if you push it, you screw everything up. And I'm able to find it. So this guy depends on the graph. If the graph is good like a tree, that number is 1. If the graph is bad like a gossip ring, that number is less than 1. Bigger than 1, which is not cool. Because the condition is the right-hand side becomes this in terms of the graph channel capacity. So this ties together the topological entropy and the graph channel capacity, which is a new method of looking at the relation of local dynamics and graph communication topology. You can tell that at some point I gave this lecture in China in Guilin. So local optimality gives global stability. That's what I've just showed you. Now, let's talk about globally optimal design. And what was the point back there back there, I picked a performance index, a local performance index. I'm worried about my energy. She's worried about her overshoot. He's worried about his fuel. We're all picking different local performance indices. So what if we want the whole formation to behave in a globally optimal manner? For example, cool movie that Tansel's students showed, you got 6 little guys in a triangle formation, they need to go through the door. So that triangle don't fit through the door. So they got to go into a line to go through the door, then they can go back and do a triangle. So that's globally optimal behavior. That's not the same as what I was just telling you about. So how do we get globally optimal behavior? It's not easy. Because if you do the graph Laplacian, if you just block all the systems together, you get diagonal matrix x1 dot is ax1 plus b1 u1, x2 is ax2. So there's a diagonal matrix of a's, a diagonal matrix of b's, and you pick a global performance which depends on the global error, not the local one, like I showed you before. What you get is you solve a huge Riccati equation that depends on everybody, and you get a u out of MATLAB routine LQR, which is not cool, because you cannot implement it in a distributed fashion. To implement that, I need to talk to everybody in the room. Well, that can't happen. I've only got 2 neighbors. So the globally optimal design is not distributed. To be distributed, you have to have L plus G Kronecker on the left. This is the graph topology, that's the local design. So if I want globally optimal behavior of the formation, I cannot get it by using a distributed control law where I only am allowed to talk to a few people. I got to talk to everybody. If I wasn't being recorded, I'd make a joke there too.
We can stop recording.
No, that's okay. I was going to make a joke about people who tweet Twitter all the time. Okay, that's the, what's it called, the Copala in Tibet. Now, let's talk about another cool deal. Output feedback. Now you're not allowed to feedback the states, you're only allowed to feedback y equals cx. So I've got each little guy can only do an output feedback controller. If you look at an airplane has 12 states. X, Y, Z position, 3 velocities, 3 rotations, roll, pitch, and yaw, and 3 angular velocities. And every airplane's got 12 states. Don't matter if it's a Cessna 150 or a Boeing 757, it's got 12 states. Basic aerodynamic states. And I've only got 4 inputs. I can pull the back stick, which makes it do this. I can screw with it left and right, which does the aileron thing. I can do the feet thing, which makes the rudder move, and it makes the airplane yaw, and I can put thrust. I only have 4 controls on any airplane. But now, you can't usually measure all 12 of those states. You can only measure certain ones of them. So you can't feed back all the state information to control the system. So now, what's the deal? Now I can't do x minus x. I have to do y minus y. I can only see her velocity and her heading. I can't see her fuel condition or how much gas she's got, all that stuff. I can only see 2 things of her dynamics. And I'm only worried about 2 of mine, heading and speed. So how do I feed back only partial information and still get the formation stability? So now if I do what I did before, using Eij of yj minus yi, y0 minus yi, if I can see the leader, then I get weird thing. The error now has L plus G Kronecker on the left and C on the right. That's a Kronecker product. And it tells how the local dynamics mixes up with the graph. So the graph limits your communication by the L plus G. That's I can only see those 2 people. And that means that I've got to respect L plus G eigenvalues when I design my controller. Moreover, I can only see part of my internal state. So this makes it obvious that the graph limits the behavior limits your information in the same way that output feedback limits your information. Output feedback limits what I can do locally, and that L plus G limits what I can do as a group. And they both have exactly the same effect. I cannot feedback all the information I want to feedback. So there's a thing called H-infinity control. H-infinity control means you have a controller and you have a disturbance trying to screw you up. And supposing that everybody, you have a graph with blue arrows and red arrows. The blue arrows are the controls at every node, and you've got red arrows at every node also. And the red guys is like wind gusts trying to screw up the dynamics. By the way, I wrote a book on aircraft control with a guy named Brian Stevens. At Lockheed, this is a joke. And he had a British accent. And he called me up once and he said, I want you to come do some consulting for Lockheed. And I said, okay, what's your problem? And he said, we have ghosts in the airplane. And I thought, what the hell? He's got ghosts in the airplane. Well, he was trying to say gusts, wind gusts, right? I thought he was talking about ghosts. By the way, you know what a consultant is? It's an engineer with a briefcase and no job. So that's what he did. So the wind gusts can seriously mess up the behavior. So there's a disturbance that's local and a controller. Basically, it's a good guy and a bad guy. And you have a performance index, and the controller is trying to minimize the energy, and the disturbance is trying to mess you up, maximize the energy. So you have a min-max design problem, and the balance is a saddle point. I'm trying to minimize, he's trying to maximize. It's a horse saddle. And that point in the middle is called Nash equilibrium. And it's okay as long as in every node of the graph, the disturbances are not correlated. If you have a disturbance at every node, no problem. You can locally reject it by using H-infinity design, which everybody knows how to do. But as soon as the bad guys in two or more nodes start talking, then you've got correlated adversaries. Then you've got two leaders. The good leader you're trying to follow and the bad red team, who might communicate over a different graph topology than the one you're using. You might have a graph I described to you before. I talk to them, I'm trying to make the formation go, and the red guy comes in and taps into some other disturbances, and the disturbance communicate by a different graph topology. You've got two graph topologies interacting, the adversarial graph and the protagonist graph. So if that starts happening, you can't just do locally H-infinity design anymore. You've got to do control of malicious adversaries. That guy there wrote some nice papers about that, and I got into this based on his papers. Rejecting malicious sensor attacks and actuator attacks in multi-agent systems. So what's the point? So if you have a single agent system, if I have a disturbance, an output, I have this usual Riccati equation I just showed you, but there's an extra term that I have to stick in because I can't measure all the states. And that extra term comes into here also. This is what you would have with state feedback. But if you can only measure your partial states, you get the extra terms you got to take into account. MATLAB routine LQR don't do that anymore. You've got to have your student write a special routine for that. So the point is that output feedback design, which means you got limited information, which means you have some thing that's trying to mess up your communication. It's exactly the same structure as a disturbance trying to mess you up. The solutions are the same. Output feedback design and H-infinity disturbance rejection. They're the same. Moreover, I could give you a theorem that says if I do output feedback on a graph, everybody uses a local output feedback measurements. I can only measure his heading and velocity. I don't know the internal 12 states of his airplane. So if that happens, then you end up with this L plus G, the graph limiting you, and here is the local controller limiting you. That's the total limits on your control. And the theorem says A minus C lambda BKC has to be stable. for every lambda. The lambdas are the graph topologies. And you get a similar theorem that says that I had before. You've got to solve this Riccati equation. The output feedback is this. The graph is this. The graph limits you through here. The local output feedback limits you. And if you can do that, then you're stable on any graph. Now, let me see what else I want to show you. Thankfully, not these slides. I'm just kidding. Now, what time do you want me to stop? 3? Just kidding. Scaring everybody. 2? 10 to 2.
It goes up to 2:15, but
I won't go that long.
you could finish whenever you want.
Okay, I'll finish now.
But probably.
Okay, then there's time for me to tell this story. How many Chinese people are in the room? I just met Ling Ling Fan. She's not here. So, there were a whole bunch of guys who lived at about 400 or 500 BC who basically shaped modern Chinese philosophy. There was a guy named Kunze, whom we call Confucius because we can't speak Chinese. There was a guy named Lao Tzu, which means old sage, and he wrote the Tao Te Ching, which some of you may be familiar with. And there was a guy named Mengzi, whom we in the Western world call Mencius, and he was very instrumental about 1200 AD, back when we started coming into the Renaissance. People started listening to Chinese philosophers, Silk Road and all that stuff, you know, the communications along the trade routes. And there was this guy named Sun Tzu, and he wrote a thing called Bin Fa, which we translate as Sun Tzu, the art of war. But Bin Fa don't mean art. It means algorithms. So his actual book is Algorithms for War. He knew how to win the war. And he gave a thing that if you follow these steps, you'll win the war. It's not an art. So these guys all lived in the Warring States period, which was the most bloodiest. Do we have time for this? You guys want to hear this? Bloodiest period in Chinese history. It lasted for 400 years, and yet it was the most culturally productive. So that was interesting. Why did that happen? So I will tell you that. But I want to talk about, there were four or five neighboring states, and these guys were all competing for the same resources. It was a multiplayer game, and these two guys were friends, these two were friends that these guys hated. They only talked to a certain subgroup. So now you've got optimal design. Everyone's trying to optimize their own performance, but you're on a graph. I can't talk to everybody in the room. Standard multiplayer game theory assumes I can talk to everybody, but you can't. You can only talk to certain people. So we want to bring together multiplayer games, such as the multiple warring states of this guy, and the communication topology. Bring those two ideas together. Manufacturing is the interaction of multiple agents. Many machines trying to work together. One guy's trying to minimize how much energy it uses to grind the rocks. The next machine says, you got to make them at least as small or I can't use them. But I don't want to be using too much resources. So the resource minimization comes up with the performance constraints between the agents. It's a multiplayer game. And the graph is the flow line, how they're connected. So it's not going to take much longer. It's like 5 more minutes. So you can go. A xi plus b ui, everyone's got their own dynamics. And then you have a performance objective that everybody has their own performance. So I'm back to the first. I realize that globally optimal design doesn't work too good. So I'm now going back to multiplayer games where everyone is trying to, has their own dynamics. You're trying to follow a leader. You're trying to make a synchronization error small. You're trying to match your neighbor's states. And if you can see the leader, his states. So you have an objective to synchronize the formation, but also you don't want to use too much energy, fuel, or time, or whatever. So you have your local performance. So this is the situation. I've got dynamics and performance index at each state. Does anybody do game theory in here? multiplayer game theory. It's really cool, you should look at it. You look at that and guaranteed 5 journal papers, no problem. If you bring that together, some of the stuff that your students are doing in the lab, bring it together with multi-agent game theory. So the deal is, everyone's got their own dynamics. If you have standard game theory, you have one dynamics, and everyone's got an influence. Example, the stock market. There's only one stock market, but everyone's trying to buy and sell, buy high, sell low, whatever the thing is. It's not the same as this. This is like an individual agent control problem. Everyone has their own dynamics, and you have a graph topology. I had a student in my class, worked at Lockheed, and I taught this class on distributed control and intelligent control, and we talked about the stock market and the Bollinger Bands and a few things that you can use to examine the behavior of the stock market. And he sent me an email about 6 months later and said, hey, I'm using that stuff you showed me. I wrote a neural net that learns the behavior of certain stocks. And I said, are you making money? He said, not much, only enough to pay the education of my 2 daughters. So that's a hell of a lot of money. So some people have used neural nets at the stock market. So now, what you can do is, and the reason I like optimal control so much, by the way, the Nash equilibrium does not work for the graphical games. You've got to redefine Nash equilibrium. It doesn't work for graphical games. You have to add an extra condition. So, the reason I like optimal control is, one, it guarantees you performance in a graph topology, which I showed. But 2, as soon as you have optimal control, you can do something called reinforcement learning, which means I can learn optimal control solutions online in real time by simply measuring the behavior of my neighbors, their actions, and I don't need to know their internal dynamics. So you can use reinforcement learning to learn optimal control solutions online in real time with data-driven optimization. So that means if her dynamics change, she burns fuel, car moves faster, I don't have to know that. I just look and see that she's driving different. And I can update my performance based on that. So as soon as I can do optimal design, I can do reinforcement learning, which is a totally different topic. So here's the gist of it. If I take the performance index and differentiate it, V dot, and use Leibniz's formula, I get something called a system Hamiltonian, which is very important in physics. And it takes 3 lines to do it, and I don't have time to show you right now. The Hamiltonian is the thing that brings together the system dynamics and the performance objectives into the same object. And it's the basis for Hamiltonian mechanics. So if you have that, I can use the stationarity condition, dH by du equals 0, theorem, that gives the optimal control. If I can find the control that minimizes the Hamiltonian, that's the optimal control. If I differentiate that with respect to u, I get this. If I put that in here, I get this horrible thing called the HJ equation, or the Riccati equation. And I don't want to solve that. So instead, I can iteratively solve that. I can try, jack around with my, I'm looking at these 2 people, jack around with my control and see how they respond. And based on how they respond, I say, okay, well, she's trying to do this, he's trying to do that. And then I change my policy. So you can repeatedly sample the environment and just see, I can kind of estimate her performance objectives. And you do this in your relationships all the time. Your girlfriend is acting a certain way, you know that she's in a mood, or your boyfriend's acting weird. We do this all the time in our social behavior, and it's called reinforcement learning. And we can learn optimal strategies by the way we interact with the people around us. Same idea. So the idea is that I can solve the multi-agent game theory problem by using reinforcement learning, which I'm not showing you how to do that. It's more behind in the slide. But I get something called multi-agent learning techniques. So many agents can learn together even though their objectives conflict with each other. So there's a lot that can be said behind that. You know what those birds are doing there? They have an iron ring around their neck. And they go down and get a fish, and every 10th fish, the guy opens the ring and lets it eat it. So this is the cormorants. Okay, so that's all I wanted to say then, and thank you very much for being